and he's going to give us like an overview today of Laney as well as his pipeline that we're going to be practicing on tomorrow. So I'll leave the floor to him.
Thanks a lot. Yes, so I will talk about Laney and Afni, and I will also I will explain what I will talk about in a second. Before, I want to thank everybody who helped with this. First, I want to thank Farouk and Rainer. So while Laney was originally developed by me, it's now mostly being maintained and further developed by Farouk, who is an employee by Brain Innovation. So Laney has received a lot of support, kind of full salary for many, many years via Farouk. I want to thank Lasse for the help with the Nordic script that we might need to go through if there's interest tomorrow. I want to thank Paul Taylor for his help with motion correction scripts, specifically for SLAB, selective layer-dependent fMRI data. Stephanie for being a beta tester of this data set, Marco for the open science stuff, and Gang Chen, if we will get to it, for the statistical analysis of layer-fMRI that we will go through. So I will first talk about why I'm excited about this workshop, the opportunities that I see, and the second of the 4 segments of this presentation will be an introduction of the data that we will all going to be using tomorrow in the hands-on session, because at this time the workshop, the hands-on layer-fMRI analysis workshop, has the unique feature that we're all working on the same data. So you can kind of see how each kind of software or each perspective of looking at those data is uniquely tuned for a given aspect of layer-fMRI analyses. I will introduce Laney, which is a software suite that will be at the core of the hands-on tomorrow. And then I will also go through a few specific comments of layer-fMRI analysis choices that I made in the analysis at the end. So as both Luca and Jonathan already mentioned, John, it is a field that's increasing. These are the papers of human layer-dependent fMRI. And while John is right in the sense that it's a new field, it's kind of, the popular application is new. It has been done already 25 years ago. It never really caught on until maybe about 2015, and then we had this exponential increase, specifically also the method, the application, not only the method in blue, but also the applications in red. And you have seen these iconic images of various applications of very high resolution fMRI in humans. When you look at the history of this field, I think there are different epochs. Specifically at the beginning, it was mostly focusing on method development on hardware, like getting to higher fields, getting to multi-channel RF coils. As soon as that was kind of settled, the method developers were still focusing on acquisition aspects like the different contrast, spin echo, gradient echo, Vasar, and so on. And then as this is mostly settled, there's still a lot of development going on in acquisition with respect to readouts, kind of advanced sampling methods, mitigating artifacts, and so on. And as this is more maturing, there are more standardizations, but also streamlining to make it more robust for large end studies as well. From the perspective of basic cognitive neuroscience applications, layer-fMRI has been, I guess, introduced by Ravi Menon, who showed kind of blots of fMRI with respect to kind of sampling across cortical depth back in pretty much 25 years ago. The first layer profile, though, was coming much later, 10 years later, from David Ress, and the first basic cognitive neuroscience applications of layer-fMRI circuitry with respect to feedback was from Cheryl Ullman right here at CMR. And this was still at early sensory areas, which then moved on to being more used across the cortical areas. With respect to layer-fMRI analyses, I think the first decades were really just having custom tools where everybody did their own thing, which is still going on to some degree. The first real pipeline, I think, was coming from John in 2010, pretty much almost at the same time as the 3D grids from Rainer. The next milestones, I guess, in acquisition, in analysis were the equivolume principle, which got a lot of attention, which then moved on further towards streamlining. Laney, the software package that I will introduce today and we will use tomorrow, is the new kid on the block. It's relatively new, first cited in 2019. when you look at this curve, you can see that we had this rise. However, it's kind of not really exponentially further increasing. We are kind of getting saturated, and there might be a couple of reasons to that. If you go to societies like OHBM, I guess the customers that the method people want to be attractive to, you get a lot of feedback on kind of how the field of layer fMRI is seen. From the outside, I think we are being seen as not having any agreement on how things are done. People are afraid to go into the field because we are fighting so much, and there's no way how to do it right? You need to pick schools, and which is not true. I think those are false contentious issues. Yes, we fight about contrasts and whether you do denoising or not, and whether MVPA resolves the vein problem or not, or whether you should do these deveining problems and whether they make things worse or not. The equivolume, equidistant controversy that got a lot of attention, or are you allowed to resample more than once? There are these things that are perceived as being kind of rules, and they're hard, and then people are afraid to move in. Whereas if you kind of look at it from the bigger perspective, and I think one of the messages we can get home from this workshop is that it's not that bad. You can get the right neuroscientific answer no matter which method you're using. You just need to know what you're doing and do it right. There are many ways on how to do things wrong, but independent of sequence acquisition or independent of the software analysis, the pipeline that you're using, you can get the right neuroscientific answer. Other things that are, I guess, also coming down to John's point of the feedback in the early visual cortex, there is this kind of perception that fMRI, but also layer fMRI, is not always perfectly reproducible. And specifically in the OHBM community, this usually comes along with kind of science policing, that we need standard analysis pipelines. You should not be allowed to tweak your things, which I think would be the end of our field. So I would like to put those two, phrase this as different questions. Yes, it's sometimes hard to reproduce the layer fMRI profiles. For example, when you look at something as simple as attention effect in V1, right? There are some people that say it's the middle and upper layers. Some people say it's upper and deeper layers. Some people say it's actually mostly the upper layers. Some people say there's no layer effect, it's just a global scaling. Some people say it's the deeper layers, and some say statistically it's the middle layer that's the only significant one. The clue here is that they're all using the same method. They all use Gradient Echo Bold with vertex-based layerification. So we shouldn't point to the method. We rather should point to what does it mean, like all these nuances that John mentioned. That kind of attention effect in V1 is a pretty general term, right? They all use different tasks. They all look at different aspects of attention. Whereas when you look at the reproducibility across methods, for example, looking at the double hump in the motor cortex, you can get that with CBF, with blood flow, blood volume, a mixture with Gradient Echo Bold with phase regression, or spin echo grace. No matter if you do vertex-based or voxel-based layerification, you can see that. So I think overall I want to bring across that there are a lot of methods out there that you can pick and choose from, and if you use them right, you can get the right neuroscientific answer. So in summary of why I'm excited about the workshop, I see that this workshop, specifically as we're working on the same data, has the potential to show you what's out there. There are a lot of different the different tools out there that complement each other. So we're basically trying to give you a repository of what's out there that you can pick and choose from. We also want to give you a feel of kind of what it entails to do a layer-dependent fMRI analysis. Last week I was reading this paper, Double-Digit Impact Factor, where they say data were analyzed using AFNI FreeSurfer, ANS, SPM, and MATLAB. And then specifically about the layers, they say 8 cortical layers were calculated using AFNI, SUMA, and custom Python code. Right? What does it mean? How do I reproduce that if I download their data? Can I kind of reproduce what they did? Probably I can, because they publish all the code, and you can reverse engineer their 100 and 1,000 lines of scripts. But we want to give you an idea of kind of something in between that you in your mind can visualize kind of why do they use so many software packages, and kind of that it's a patchwork usually in layer-dependent fMRI, and that there are some basic steps that you need to pay attention to. So that's something we can bring across at this workshop. And there are many choices we need to make along the way, and ultimately you can get the same thing if there are many different ways to get to the right answer at the end. In practice, very specifically, this means that we will start with a data set like that. We have a time series of fMRI data, and we want to convert them into something like that, into a layer profile or a layer profile modulation that ideally has a little star over here that's significantly statistically significant. So this is, I guess, the goal that I want to go through tomorrow. Okay, let's introduce the data. And I want to do so by, again, coming back to the history of layer-dependent fMRI, because layer-fMRI is obviously a wide and increasingly diverse field where different people care about different things. The new thing this year is that we have one data set that's being used for different analysis pipelines, which was a hard lesson that we learned 2 years ago, that some analysis pipelines require certain data that not every data set has. So we acquired this data set for the sole purpose of a workshop to have this as a tool. That's kind of representative. And so we looked at the history of layer-fMRI paper, and I think I would like to divide that into kind of two sub-areas or sub-periods. So there's the period before COVID and after COVID, which is almost the same number of papers. And across history, we see that the sample size, N, is increasing, as John mentioned, but also the fraction of studies that make the data publicly available is also increasing. And this puts some pressure on which data set we want to use for such a workshop, because you cannot manually segment the entire brain for what do we have, like 60 participants, right? Or many data sets. So we need to have something that's kind of pipelinable, which doesn't really reflect my work at all, right? I'm an acquisition person. I want to have something that's quick and dirty. I want to finish my scan tonight and look at the layers half an hour later, so I know how to change my task or my acquisition on the next morning. So different layer tools are tuned for different things, which is another take-home message I want to bring you across. However, this data set needs to fulfill to be somewhat pipelinable. Also, as we're moving along, as Jonathan said, the readout, the sampling scheme changes a bit. Specifically after COVID, the number of papers that use 3D encoding methods is the majority. So different than last the 2 years ago workshop, we also use a 3D EPI readout now. And the analyses that are being used is a patchwork. So there are many different analyses that are tuned for different things. So we need to have a data set that can be fulfillable and pipelinable or pump through different analyses with all their different purposes of how they're and why they're being built. So we needed to have a data set that any analysis can work with. And of course, keeping in mind that data acquisition and analysis are not separate things, right? Usually you acquire, you make your acquisition choices based on a certain analysis in your back of your head. For example, myself, in the last 50 scans that I acquired, I didn't acquire structural reference scans. And because I'm after different things. However, other layer-fMRI analysis pipelines need these structural reference scans. And so it's not independent. So it's kind of an artificial case that we are simulating here. Also, the fraction of layer-fMRI papers that not solely rely on gradient cobalt, but also use something else alongside to kind of inform the interpretation of the gradient cobalt is also increasing. So we didn't want to focus on gradient cobalt only, but also have non-bold aside of it that you can use or not use. So this is the data set. It's from a Siemens 7 Tesla scanner, acquired with a standard 32-channel Nova coil. It's a PTX coil, even though we didn't really use PTX for the fMRI for that matter. We did use it for one of the structural reference scans. It's a 3 EPI at 0.8 millimeter resolution, which based on the statistics of human layer fMRI papers out there is, I guess, some sort of a standard. With respect to coverage and TR, I made some compromises here. So we wanted to have something that has enough coverage that it gets you most of a brain area, like for example the calcaneal sulcus in this case. However, if we want not only gradient cobalt but also vaso, the volume acquisition time is more than doubled. So the effective temporal resolution ends up being more than 3 seconds. It's less than 4 seconds though, so you're still in the regime of the hemodynamic smoothness of the HRF. So it's a compromise here. We have relatively little coverage and then also relatively long TR at the price of having both bold and vaso in there. Specifically, based on the experience from 2 years ago, we now have spectrum of different structural reference scans. We have the MP range, PTX MP range that is also illuminating the bottom of the brain slightly better. The MP2 range, which seems to be quite popular in the field out there, but also distortion matched structural reference scan T1234 for people like Cheryl, if she wants to use that data set as well. From the functional paradigm perspective, we have a flickering checkerboard. It's not the entire visual field. It's kind of relatively small, so there are areas around it that are not activated. We have 6 runs. Each block within each run contains of 8 TRs. And so with the TR that we had, this means that each trial is 29 seconds. So 29 seconds rest, 29 seconds flickering, rest, flickering, and so on. And we end with another rest period. And the same thing 6 times. So you can also conveniently average this if you want to. The last 2 scans, the last 2 volumes are reference noise scans. So there was no excitation pulse there, it was just pumping noise through your analysis, so you can see the spatial heterogeneity of thermal noise. We have magnitude and phase data, so you can use phase regression if you want. You can use complex valued Nordic if you want to. So the data structure, you can download it from the Harvard Dataverse, but also now we learned that the dataset increased quite a bit, so you cannot just download all in one button. So in the email that was sent to you, there are several mirrors as well. So on Zenodo there's a dataset, but also on Dropbox and G Drive where you can download the copies. There's a certain folder structure where I myself have kind of files within folders and the scripts that are being used on those files in that same folder that we might make more sense as we go through it tomorrow. Then also Rainer has a subfolder with everything nicely encapsulated within that folder, and similarly Anna will work similarly on the server tomorrow. I very often care about acquisition methods and want to kind of see how sharp my layers profiles are or how they are different across resolutions. And many cognitive neuroscientists care more about how layer profiles are modulated. So we can use this data set to look at modulations as well. So for example, we can look how layer profiles are different between gradient bold or vaso, which very often are dominated from layer 2, 3, or 4. But then they are mostly different at the most superficial layers, partial voluming of the higher veins. You can also ask interesting neuroscience questions on specifically neurovascular neuroscience questions. If you look at the HRF, for example, we will see that we have multiple kind of peaks, this main peak and then also the posthumous undershoot, where there are quite a number of layer-fMRI papers out there already that say that for the main peak you have this roughly linear increase towards the surface, a bit superlinear sometimes, whereas for the undershoot, it's really, really dominated from the surface, not just linearly, superlinearly. So it's basically the surface and almost nothing else. Some people see that there's a tendency also at the deepest layers. Similarly, for kind of surround inhibition effects, you can look at these negative areas outside the flickering checkerboards, which are tiny, but we are expecting a similar layer profile for those negative areas as for the undershoot period. Tomorrow I will mostly focus on those two as an example. John mentioned that it's very hard for people kind of to go to the scanner and crank up the resolution, and then sometimes if you're a newcomer, you need to charge. Is this normal now? Yes, of course it's layer, so it's supposed to be noisy, but what is too noisy? So aside of this data set that we are working on tomorrow, there's a subfolder in that data set of other data worth browsing. So there's an example of larger coverage vaso, there's an example of 2D multiband visual focused protocol. I think this is from Kendrick Hayes' critical vein paper from a Siemens scanner. There's also a Philips 3D PI data set where you can see the unique features, how Philips is different, namely that you have kind of quite nice SNR right over here, and then quite suddenly from one voxel to the other you have this higher noise level as from Sense, right? Because in Siemens, usually when you use grappa, you have more smooth distributions of the noise pattern. But there's also one data set also on kind of trying to give you a feel of kind of what the limits are. So this is a data set with 0.3 millimeter isotropic of 18 slices to kind of see what you can see and what you can't see. And also in the activation map of those. So browse that if you want. All right, Lainey. LaNY stands for layers and nifty, so it's a C++ suite, and there are multiple C++ programs that you can run in the terminal, and they're all based on nifty. So you give it a nifty and it spits out a nifty. It's now mostly maintained and co-developed by Renzo Huber from Ranna's company. The specific niche that LaNY is filling is that it's working with weird data. I would like to introduce this with this beer wine metaphor here. So there are things that are streamlinable, specifically conventional, low field, 3mm fMRI, have things like fMRI prep. It has been developed over decades and it just works in a Henry Ford assembly line production. You can do this across tens of thousands of participants. You don't have a lot of variance, and it's reproducible in the sense it's homogenized, right? Heineken here tastes the same as in my home country. In summer or winter, you don't care, right? It just is very stable. This is different for wine, right? Wine is not worse, right? Or wine is not less reproducible. In order to maintain a high reproducible quality, you need to tweak it based on the weather that year and based on the different geographic locations there. So LaNY is trying to deal with the weird data that cannot be encapsulated in multinational brands of corporation. What I mean by that specifically is that you can basically take a screenshot of your paper and then make a 2D layer out of that and just block the gray values of that. You can run it through distortion matched whole brain and EPI data if you want to. You can just draw something on 2D and run LaNY on it and put it on your t-shirt if you want, or these ex vivo slices that John also showed. And you can take them, it works in 2D or 3D, specifically also with the question of lower brain structures, right? You cannot, you don't get layers from recon all if you are interested in the amygdala. But the amygdala does have these kind of different nuclei that are kind of linearly aligned. So you just can kind of pick your borders and then estimate layers in the amygdala or the superior caniculi, which has this very kind of directional angio-architecture, specifically towards the surface. But also you can use it on weird data like a cat visual cortex, like from CMR. At this workshop, I will still focus on a weird data set. For example, on something weird in the sense that in layer-fMRI, we usually only cover part of the brain. So we do not necessarily fulfill common topology requirements of closed surfaces without holes. So LaNY can kind of work with that without requiring fiddling of the distortion correction or alignment for that matter. Right. So the niche is that it's kind of nifty in, nifty out. It's a program that usually starts with ln. You have some options, input and output. And we will do that. Maybe just to get a bit of a feeling of what I should prepare tomorrow. Who has worked on a terminal before, typing in commands? Okay, most of us. Who has not worked in a terminal before? Okay, we will get there. Then the things that LaNY is kind of known for or used for are things like the layerification, converting segmentation files into layer files, specifically with respect to the equal-volume principle that John introduced. Some people use it also for kind of columnarization of basically chunking up the brain based on layers that are pre-computed into kind of sub-columns and smaller patches. If you build topographical relationship with those, you can also kind of look at patches of the cortex that you flatten out to look at topographical representations of like digit maps or something, which is doable, but it's not really the major tool that LaNY is used for, outside of the developers maybe. Some features that got some attention over the last years, which is kind of dying down, interestingly, is the deveining. So if you assume that your cortex is always trained towards the surface, you can use this assumption as Maki Irati showed in David Norris's group. And based on the columns and the layers that you pre-computed, you can do this based on a column-by-column basis and try to get rid of this superficial bias in creating the cobalt based on different assumptions that you make. At the cost, however, that you're basically throwing away 80 to 90% of your signal. So it will look noisier. So it's a question of whether you want to do this in the volume, or if you rather want to do this in Excel in your layer profiles later. Other things that I think got a lot of attention early on was something like layer-fMRI smoothing, that you can use kind of very, very noisy 0.5 isotropic data like this one, and then just smooth the hell out of them by having the assumption that neighboring columns are doing the same thing. This has not been used as much. It's more kind of for exploratory purposes, and maybe Nordic came along and to solve that issue, or solve the same problem why people did layer-fMRI smoothing. There's a lot of material out there. Specifically, there's the layer-fMRI YouTube channel that has playlists, where specifically for Rook is now having new features like the Laney Talk podcast style, and talks on Laney. He presents new implementations and like programs of Laney there, but he also has this, I'm not sure if you can see this, the Let's Analyze series, which is really useful, where you kind of, whenever somebody comes to him and throws some data at him and says, oh, how do I deal with that? He just records himself doing the analysis and then puts it in YouTube. It's a huge resource. And there are also these blogs that semi-professionally also explain what the basics of the algorithms are that are implemented in Laney. And of course, the code and download instructions on GitHub. Okay, so I have until 11:40, right? Okay. So there are certain decisions along a layer-fMRI analysis pipeline that I want to justify, and which is now the last part of the presentation. This is the acquisition pipeline that I envisioned for tomorrow. We can start with Nordic denoising. Actually, I was thinking of skipping that because it requires MATLAB that not everybody might have. And also we don't need it specifically. If there's specific interest, we can decide to go through that as well. Then there's the motion correction or alignment across the different volumes within the runs, but also across the runs. And then we want to convert these time series into activation maps. After that, we will do segmentation, meaning kind of defining the tissue borders between gray matter and white matter and gray matter and CSF. And then coming to the core of the layer-fMRI analysis pipeline, the layerification, basically converting those segmentations into layers. We will then extract the signal and also do statistics on them to see how different layers are statistically different from each other if we get to that. If there's a lot of interest, we can also talk about alignment, on how I do alignment of these thin slabs to a kind of whole brain reference scan. Nordic is the first step that is included in the online version of this tutorial that I recorded last week. So if you will not get to it tomorrow, you can check it online. It's basically converting data time series that look like that into data time series that look like that. And I'm not sure how that comes across nicely. So Nordic basically removes anything that looks like Gaussian noise. So if you have a single voxel that has a unique time course different than voxels around it, this is considered as noise. Maybe that voxel has kind of just Gaussian-like looking time courses that are different than anything around it, and that's an interesting signal. Nordic will kind of remove that. So you see that kind of consistent sources of variance, if it's variance of interest or variance of not interest, if it's not looking like Gaussian noise, it will remain in there. And next, I will want to justify my choices in alignment that I do. And maybe I want to borrow John's way of separating kind of the alignment problem into the estimating the alignment and then do the regridding. So first we have the estimation of the alignment, where I will pay a lot of attention on the mask, basically on how did we capture this alignment. To explain this, I want to look at this conventional data set, which I think, yeah, there's motion. It's not kind of, I've seen worse, I've seen better. It's kind of representative, I think. And if you have such a thin slab, you can see that there's kind of motion not only within the slice, but then also across the different slices. If I wouldn't do any motion correction, right? If I would just take that and average it, you end up with something like this. It's not too bad, is it, right? There's structure there, right? So yes, there's motion, and if I pick that voxel over here, in some runs, I actually might not, might sample signal from completely different layers. But overall, the fact that we still see structure there means that this voxel has a much higher probability of more often representing superficial layers than this voxel over here, which has a higher probability of capturing deeper layers more often. So we might still be able to do layer-fMRI. Like motion is an annoyance, it's usually not a showstopper. And still we want to get rid of that motion. So conventionally, as it's done in SPM or in AFNI, that I know, usually the brain is kind of masked and then the motion is estimated within that, which is a problem, specifically also for 3D EPI methods. Because it still has these residual motions sometimes, which is coming from the fact that you have a thin slab. So the outermost slices, they have weaker intensities because of different spin history effects or also different kind of slab excitation profiles. And these different intensities in the outermost slices are not really tissue intensity differences. So the motion correction estimation algorithm tries to align these borders that are not real brain borders, but they are just acquisition borders. So therefore, if you look closely, you can see that the brain is still kind of moving up and down a bit. And this is even the best case, right? Here I'm looking at an inversion recovery EPI fMRI dataset. If I would use a Gradient-Cobalt dataset for that, that doesn't have such high structural contrast, then very often, at least in AFNI and both in SPM and ANS, in fact, it tries to move the slab completely out of the field of view, and then you end up with nothing. And I'm circling through different runs here. So the thing that I'm doing here is I'm trying to get rid of the outermost slices and give them less weight. So I'm estimating the motion only in kind of a fraction of the coverage that I have, which is then basically resulting in kind of more stable images across runs. We have these different shading patterns that are coming from different reference scans and different calibrations for each run. They are absolutely stable across time. So I don't really care about these shading patterns that you see different across run as long as the brain is stable. So now the brain is stable and it's rather this letter slip that seems to be moving up and down. And that's why we have all this weirdness on the left side, which will be the first part of the script for tomorrow. Then we can do the resampling. And John talked about this extensively. I would like to also spin it from the uniqueness of 3D EPI, which I think gives a different angle to it. So if you look at this from a pure imaging processing perspective, and you have this kind of image in your head that the voxel is a signal that has homogeneous signal within and then infinite test-limited sharp borders at the end. If you look at that, you can kind of capture the partial voluming, and if the voxel is moving, then it's at a different location. You can estimate that, put it back. However, if a voxel kind of is if the signal of the voxel is at the borders of the new grid, then you have this kind of smoothing or kind of signal loss in this perspective. You can try to account for this if you upsample, but the point I want to make is that in 3D EPI we have a different problem, because in 3D EPI we are doing like Fourier encoding. So this image that we have in our head when we think about voxel is not very intuitive. We don't have homogeneous signal with sharp borders, right? Well, in reality, we have something like this. We are not really that sharp to begin with. Maybe within the voxel we are even sharper. So in Fourier encoding, we don't have a resampling problem, in the sense that, for example, if you take this voxel, if you put it back to k-space and just add a linear phase, let's say we want to have a translation of that voxel by half the voxel size, we add a phase, put it back into image space. We add another half a voxel phase, put it back to image space. We can do this like a billion times by steps of half a voxel, and we will never lose resolution, like ever. The practical test for this has been proposed many years ago from Bob Cox. He says that you should just take a brain and rotate it by 1 degree 360 times. And then you compare the image that you started with the image that you end up with, and see kind of how lossful your resolution is. And it really depends on the interpolation here. I'm not sure if you can see this for kind of linear, which is not really capturing the true Fourier encoding domain of our distribution of our kind of point clouds with a certain distribution. There's a lot of blurring involved. And And this might be referring to the animation of the motion correction that John also showed. For nearest neighbor interpolation, you can see that it looks like it's not blurring, but it's actually even more blurring. Like, it depends what you mean with blurring. There's most local displacement. It doesn't look smooth, but the displacement is the biggest. Now, if you try to capture this Fourier kind of encoding domain with sync interpolation, animation is stopped, you might see some errors. Like, it's almost indistinguishable, and actually higher order splines can fit or represent the sync interpolation quite well. So for those reasons, I don't worry about doing resampling once or twice or a billion times. If you kind of do it once, it's the same as if you do it. In this case, this animation has been done of doing one interpolation versus doing 37 interpolation of 10-degree steps. Because it's 3D. Then we will do manual segmentation, and also John alluded to that. Manual segmentation is can be a tedious process. I do it because it's fast, because I don't need to worry about my distortion correction, I don't need to worry about my alignment. I get my data off the scanner, and within like 30 minutes I have my layer profile from it. Note though that I, as many people, are interested in small patches of the cortex. There is a debate going on on whether kind of it's okay to do manual segmentations, or if it's maybe even unscientific to do layer-dependent segmentations, or if it's the most efficient approach. And that really highly depends on the application. Do you need whole brain? Do you want to have kind of a user independent analysis, or do you want to have a different trade-off to maybe have higher quality and then lose this kind of reproducibility and user independence in there? I certainly think, copying this from Farouk here, that it's not unscientific to do manual correction or segmentation. You can in fact win a Nobel Prize with just drawing things that you see. And it of course depends on your study. Then we can do the layerification in Laney, which is the process of converting a segmentation into layers. And tomorrow we might not do the entire sulcus, which takes maybe 20 minutes to segment, but rather we might look at a few slices only. And there are a few choices in the command that we will execute tomorrow. One of them is the equivolume approach. And you saw this already from John, namely that in this case of an ex vivo stria genari, you can see that it's closer to the CSF at the crown of a gyrus, yes, to the bottom of the sulcus. So it's not perfect if you use the equidistant approach. So you need to kind of over-amplify this curvature bias there. Overall, I think the equivolume principle got a lot of attention, and maybe specifically in my circles, and it was really shown as the chosen one that will solve all our problems. When you implement it, life happens and it's messy, and then things happen, and it's more sensitive to segmentation noise. You can try kind of tweak it, specifically with respect to these edges that we sometimes have, and the curvature radius abruptly changes. So if you tweak it and work on it, and you can make the good come out at the end. However, life just moves on with or without it. Like you use it, you don't use it. I think that the fight has retired, maybe along with some people. The layer profile can be pretty similar. Specifically, the tweaking that I refer to is referring to the one parameter in the command that we will execute. Namely, it will specifically focus on those kind of artifacts. This is an example from Josine, a monkey cortex that has almost a perfectly straight cortex, and then it basically has a U-turn and goes back. Now, if you think of equivolume, you need to preserve the volume. However, it's not really telling us how big a column is. Like, how big is that volume? And if we do this on a column by column basis, the equivolume principle, then we have these step functions, right? Because now suddenly the inner cortical layer needs to be thicker. That's not physiological, and it tells us also how the equivolume approach is not it's not the ultimate answer, right? There are further developments beyond the equivolume principle if we cannot rely on the data-driven approaches just yet. So how this is implemented in Laney is basically trying to think that the curvature radius that the brain sees in this equivalent principle is kind of smooth. And the default is a smooth iteration of 100, which is calibrated based on voxel spatial grids of 200 micrometers. You want to use less if you have thicker voxels. And it also helps a lot with this amplification of segmentation noise. That might even be stepwise noise if you, which is paying the price of doing everything in voxel space. Other things that I sometimes see in the literature that I want to mention is that since the layers are not estimated on surfaces here, we have a restrictive or limited spatial precision of our borderlines. And so therefore it is advised that you do the layerification of finer spatial grid than the native resolution, aka upsampling. But because of these worries of the reviewers that they might think it might put something there that isn't there, I see people use LaNi at 0.8 millimeter, which can be done. However, then you want to use this equal counts option that I will explain as well. Basically, it tries to homogenize the kind of the inaccuracies that you have from these stepwise tissue borders. You have seen this already. We want to use more layers than we have resolution for, because each voxel covers several kind of distances from the gray matter white matter border, and if you kind of lump them together, you have an even wider kind of lump of different partial voluming. So do as many layers as your spatial grid allows. In the kind of best case, and if you have perfect SNR, you would actually not kind of lump them together at all, right? You would have each voxel centroid, and then the value of each voxel, and then plot them as point clouds, which has been done in the very, very first layer applications. And then what we are doing, though, because this is usually noisy, we kind of bin them into different partitions. And then the problem, if you don't work on a high enough resolution, is that not every distance is allowed here. You have kind of, the next voxel would be exactly half the voxel shifted, the next one would be square root of 2 of that. So you can choose the equal counts option, which is not dividing the voxel based on this discrete distances, but it's basically dividing the voxel based on the number of voxels you have available, which is, I think, also quite common in some cognitive neuroscience applications. That's all Federico now, who kind of does these histograms divisions as well, I think. If you have perfect data, you don't need to bin at all. You just plot your gray values of each voxel as these point clouds, as an example from Farouk. This makes it harder to do statistics, though. So if the most extreme case that I've seen is from Emily Finn, where she basically divides it into two kind of chunks of upper and deeper layers, because then you have kind of two tests, and you don't need to worry about the multiple comparison correction or dealing with the mess of these voxels. There is some similarities here with respect to kind of histogram binning. If you have data like that, where you have a kind of a separate sample over here, but it's also noisy, you need to kind of choose the right binning. If you only have 3 bins, you might miss that this is separated here, but then also kind of you want to average enough neighboring voxels that meet your SNR requirements. So next is the layer extraction, which and the extraction per se is pretty easy. You basically have a LaNi program that looks into the mask of the layers and then finds all the activation voxels that fall within that mask and then averages them and spits them out into a text file. And then also plots them in the little ASCII art that we will look at tomorrow. Then the question is, what do we do with that? Specifically, if we have this across runs or across people or across different task conditions. And I will show you one way that I learned from Gang Chen, which is solving a lot of problems that we have. Namely, in layer-fMRI, specifically if we work on a higher spatial grid than we have resolution for, these profiles are smooth. So we have more data points than we have independent samples. So neighboring data points are not statistically independent. Right, also we kind of don't really know kind of which layer refers to which cortical depth. And we also often don't know how statistically dependent they are. So what Gang Chen proposes is something that he calls profile tracking analysis. That's something that comes from the temporal analysis of fMRI. So in fMRI, in the temporal analysis, many of you probably know this GLM, so we basically have expectation of a certain activation and rest periods and maybe even transition periods in between that, and we try to fit that to that model and find a beta value that fits best. So Farouk made these slides basically proposing that we can do the same thing across space, right? If we have this crown of a gyrus over here, we can have kind of different voxels that we plot across a different cortical depth. And it doesn't really matter if we have more data points over here than here. We don't need to like even them out, which I see sometimes in layer from my papers out there, that they try to kind of match the number of voxels per different layers. And because then it's easier with the statistical certainty. If you do kind of more free statistical analysis, this would be easier. So what Gang Chen proposes is basically fitting smooth splines to it. And the smoothness of the spline is directly estimated based on the data, and it's used then in the statistical model. The issue with that in AFNI, though, is that the data need to be presented in a very specific format, which we will go through tomorrow. So we need to have certain tables with run numbers or layer numbers and condition numbers assigned. We need to have a prediction of it, which is basically the assumption that the different conditions are different, and then it is fitting those smooth splines and comparing them based on statistical significance. And you can actually do this on single layer profiles already, because you have the uncertainty based on neighboring points as well. Right, last but not least, the alignment, which is something we can go through if there's interest, because it happens quite often that something is wrong with the header, specifically if you use AFNI and oblique slabs, that even though the slice was acquired in oblique orientation, your viewer is not showing it, and then you can use ITK snap with some manual tweaking to get a first rough alignment and then use that alignment in further processing. For example, in ARNS, which is something that we can go through, but it's not really necessary for the overall pipeline. And that's it. Thank you very much.